Another example of OS design is what we call a microkernel. Microkernels only require the most basic primitives at the operating system level. For instance, at the OS level, the microkernel can support some basic services such as to represent an executing application, its address space, and its context, so a thread. Everything else, all other software components, applications like databases, as well as software that we typically think of as an operating system component, like file systems, device drivers, everything else will run outside of the operating system kernel at user level, at unprivileged level. For this reason, this microkernel-based organization of operating systems requires lots of inter-process interactions. So typically, the microkernel itself will support inter-process communications as one of its core abstractions and mechanisms, along with address spaces and threads. The benefits of a microkernel is that it's very small. This can not only lead to lower overheads and better performance, but it may be very easy to verify, to test that the code exactly behaves as it should, and this makes microkernels valuable in some environments where it's particularly critical for the operating system to behave properly, like some embedded devices or certain control systems. These are some examples where microkernels are common. The downsides of the microkernel design are that although it is small, its portability is sort of questionable because it is typically very specialized, very customized to the underlying hardware. The fact that there may be more one-off versions of a microkernel specialized for different platforms makes it maybe harder to find common components of software, and that leads to software complexity as well. And finally, the fact that we have these very frequent interactions between different processes, different user-level applications, means that there is a need for frequent user kernel crossings. And we said already that these can get costly.